got mountains of material heavy stuff that absolutely has to go downhill. It's just part of the job, a necessary cost.
A fundamental part of the process, yeah.
But what if that very movement, that downhill journey, could actually generate electricity for the whole mine? Maybe even make some money.
It sounds almost, well, too good to be true, maybe.
Exactly. But it's not science fiction.
No, it's really happening. Today, we're doing a deep dive into regenerative downhill conveyor systems in mining. It's tech that basically transforms that necessary movement into an energy source, an asset.
And that's why we call this the deep dive, our mission for you today, to really pull back the curtain on how these systems actually work, why they're such a game changer, and what it really takes to put one in place.
We've sifted through a lot of technical analyses, engineering docs, some really cool real-world case studies.
And we're boiling it all down for you, giving you the key insights fast. So let's get started.
Okay, so this core idea, at its heart, it's just physics. Gravitational potential energy, UMM from school.
Right. Mass, gravity, height.
Exactly. So you've got this bulk material, mass mm, coming down a height h. That potential energy turns into kinetic energy. Now, historically, that energy was a problem, a liability.
You had to just get rid of it.
You had to dissipate it, usually as heat, using massive brakes, just to stop the whole thing from, running away.
Just burning off this massive natural force. But now it's an asset. How does that flip happen?
That's the paradigm shift, right? The constant flow of heavy stuff downhill creates this force trying to speed up the belt. So to keep it at a safe, constant speed, the drive system has to apply a braking torque continuously.
Okay.
But here's the key. Instead of just turning that braking energy into waste heat, we convert it into usable electrical power. It's capturing potential versus just, wasting it.
Okay, that makes sense. But how does a normal electric motor suddenly start making electricity? Is there some kind of trick?
It's actually pretty elegant. A standard AC induction motor. It can run as a generator. It happens under what's called negative slip.
Negative slip. Okay.
Think of it like this. Normally, a motor uses power, creates a magnetic field, and pulls the rotor along, right?
Right.
But with a downhill conveyor, the weight of the material actually forces the motor's rotor to spin faster than that magnetic field. It's being overdriven by the load.
Ah, okay. The load is pushing it.
Exactly. And when that happens, the motor flips its function. It starts sending electrical energy back out instead of drawing it in.
That's clever, and obviously much better than the old ways of braking. Could you just quickly walk us through those differences?
Sure. The oldest way, mechanical braking. Simple, but super inefficient. All that energy just becomes waste heat through friction, lots of wear, dust, even fire risk sometimes.
Not great.
Then came dynamic braking. That was a step up. The motor did generate electricity, but then it was immediately sent to big resistor banks and, again, just burned off as heat. Controlled, yeah, but still pretty wasteful.
So regenerative is the breakthrough because it actually uses that captured energy.
Precisely. It's the most energy-efficient way. The generated power is captured, conditioned by the drive system, and then fed straight back into the mine's own electrical grid.
So it directly cuts down on the power they need to buy.
Exactly. It lowers net energy use, cuts operational costs. It's like a continuous energy loop.
And making this work smoothly needs variable frequency drives, VFDs, that can handle four-quadrant operation. What's the key thing about that for us?
Right, 4 quadrants. For downhill conveyors, the really important one is quadrant 2. That's forward braking or regenerating.
Okay.
It means the conveyor is moving forward like it should, but the VFD is applying that retarding torque, making the motor generate power. And modern VFDs are smart. They can switch automatically. If the belt's empty, maybe it needs power motoring. If it's loaded and going downhill, it switches to regenerative mode. All seamless.
Keeps the speed constant and grabs all that energy.
Okay, so we've got the core idea, turning this liability into an asset. But how do they actually build these things to handle massive loads? Let's kind of peel back the layers on the tech. What's the absolute heart of this regeneration capability?
That's got to be the drive system itself, specifically active front-end variable frequency drives, or AEs.
AEs, okay.
These are the key enablers, especially for high-power regeneration. Your standard VFD. Power usually just flows one way, grid to motor.
Right.
AFE drives, they're bidirectional. They have this sophisticated electronic bridge using IGBTs, these power electronic switches that allows power to flow both ways. So when the motor regenerates, the AFE takes that power, cleans it up, synchronizes it, and feeds it right back into the mine's grid.
And you mentioned AFEs have other benefits, too,
Yeah.
besides just sending power back. Something about power quality.
Huge benefits, yes.
Yeah.
Power quality is the big one. Think about harmonics. They're like electrical noise or static on the power line caused by the VFD switching.
And that can cause problems.
Yeah.
Oh, yeah. Overheating equipment, interference with controls, just bad news for the grid. AFE drives are brilliant because they inherently produce really low harmonic distortion, like typically less than 5% total harmonic distortion, which is very clean.
So they keep the mine's electrical system healthy.
Exactly. Plus, they operate at near unity power factor. That just means the mine is using the electricity it draws really efficiently. Good for the bills, good for the grid.
And the motors themselves. Anything special there?
Well, you need robust motors. High-performance VFD-grade induction motors are common. They have better insulation to handle the stresses from the drive. But for the really big systems, megawatt-scale stuff, we're seeing more permanent magnet synchronous motors, PMSMs.
Why those?
Even higher efficiency and more power dense. You get more power out of a smaller package, basically.
Okay, so that's the sophisticated electrical side. But we are talking about moving mountains, literally.
Yeah.
The mechanical systems have to be incredibly tough, and safety. Well, that's got to be paramount.
Absolutely non-negotiable. The conveyor belt itself, it's under enormous tension. You need incredibly strong, high-tension steel cord belts. Think something like the ST-7800 belt they used at Los Pelambres.
ST-7800. That sounds serious.
It is. But what's really interesting now is how advanced dynamic analysis lets engineers design these belts with slightly lower safety factors, maybe around 5.5 instead of the old standard of, say, 6.7.
Wait, lower safety factors, is that safe?
It sounds counterintuitive, right? But the dynamic analysis gives such a precise understanding of the peak forces that they can optimize the belt design more accurately. It means you can potentially build an equally safe belt using less material, making it more cost-effective without compromising integrity at all. It's smarter design.
Gotcha. And for safety stops, you obviously can't just rely on the electrical regeneration, right?
Yeah.
What if the power cuts out completely?
Precisely. That's why an independent mechanical braking system is absolutely mandatory. It has to be fail-safe.
Fail-safe meaning?
Meaning it engages automatically if power is lost. The preferred setup is usually low-speed disc brakes with calipers that are spring-applied and hydraulically released.
With spring applied.
Yeah, the springs push the brakes on. You need hydraulic pressure to pull them off, so if you lose power or hydraulic pressure, bang, the springs automatically engage the brakes. Inherently safe.
Okay, that makes sense.
But here's the really clever part. Modern systems use intelligent soft braking controllers. These are PLC-based. They use proportional hydraulic valves to apply that braking force gradually, smoothly.
Why gradually?
To avoid dangerous shock waves. If you just slam on the brakes on a long, heavy elastic belt, you create these massive transient tension waves that can just rip the belt apart or cause other damage. Soft braking controls the stop, ramps the torque carefully, minimizes those shock waves.
So it's not just stopping, it's stopping smartly to protect everything. And I'm guessing reducing friction everywhere else also helps generate more power.
Oh, absolutely. It's a direct link. Optimizing all the other mechanical bits for low friction isn't just about general efficiency. Every bit of friction you reduce means more net power available for generation.
Like what kind of components?
We're talking high-quality, low-resistance idlers. Those are the rollers the belt runs on. Using the right grade, maybe larger diameters, optimizing the spacing between them, stuff like that. And active take-up systems, too, which keep the belt tension just right under all conditions, prevents slip, maximizes power transfer.
And managing all this hardware.
Mm-hmm.
There's got to be a brain coordinating it all.
Exactly. That's the control and monitoring system. The PLC, the programmable logic controller, that's the central brain. It talks to everything. The VFDs, the soft braking system, it manages speed, load sharing if you have multiple motors, coordinates those complex stopping sequences.
And the operators see all this.
Yep, through the SCADA system, supervisory control, and data acquisition. That provides the HMI, the human-machine interface, gives operators a full view, real-time data, alarms, control capability, usually from a central control room.
And this system isn't just about running things, it's also about keeping them running, right? Predicting problems.
That's where condition monitoring is key. These systems are loaded with sensors, measuring bearing temperatures, motor vibrations, belt alignment, pulley health. You name it.
Collecting data constantly.
Right. And that data feeds into predictive maintenance systems. Algorithms analyze trends, look for anomalies, flag potential issues before they cause a failure, allows for proactive repairs, maximizes uptime. It's smart asset management.
Okay, so what we're painting a picture of is this really sophisticated mix of mechanics, power electronics, and controls. This definitely isn't just, sticking some motors on a downhill run. The whole design process must be way more involved now.
It absolutely is. Designing one of these regenerative conveyors is a serious systems engineering challenge. It's moved way beyond simple static calculations. Advanced modeling and simulation are basically mandatory now.
How do they even start? Going from just an idea to a full blueprint?
It often starts with the route itself. They use really detailed topographic data, maybe from LiDAR scans or drone surveys, to create these super precise 3D terrain models.
Why is that so important?
It lets engineers design the conveyor to follow the natural curves of the land much more closely. This can massively cut down on civil engineering costs, less need for huge earthworks, tunnels, or bridges. And often, it means you can have one single long conveyor flight instead of multiple shorter ones with transfer points.
Fewer transfer points means more reliability, fewer places for things to go wrong.
Exactly. A single long flight is inherently simpler and more reliable.
Okay, route planned. Then you get into the power and tension calculations. How do they figure out if it's actually going to generate power or if it might still need some help?
That boils down to the SEMA formula for calculating effective tension, which we call TIA. On a downhill run, the weight of the material going down actually helps pull the belt along, so it reduces the total tension the drive needs to overcome. And here's the key. If the downhill force from the material's weight is greater than all the frictional forces trying to stop it, the total effective tension to lid actually becomes a negative number.
Negative tension.
Well, a negative effective tension. It signifies that the drive system doesn't need to push, it needs to hold back, it needs to provide a braking torque. And that means the system is in a regenerative state, generating power.
And the amount of power.
Simple calculation once you have that negative T. Power in kilowatts is just T in newtons times the belt speed in meters per second divided by 1,000. A negative power value means you're generating.
Now, this is where you said things get really interesting. The shift from static analysis to dynamic analysis. Why is that absolutely critical for these big systems?
Right. Think about a really long conveyor belt. It's not like a rigid steel beam. It's more like a huge, heavy elastic band.
Okay, stretchy.
Very stretchy and with a lot of inertia. Static calculations assume it's rigid. They're fine for steady state running, but they're completely blind to what happens during sudden changes like an emergency stop.
And that's when things get dangerous.
Potentially, yes. If you slam the brakes on that long, loaded elastic belt, you create a massive tension wave, a shock wave that travels along the belt. These peak transient tensions can be way, way higher than the normal running tension.
High enough to break the belt.
Absolutely. Or damage pulleys, structures. Static analysis just doesn't see these peaks. Dynamic analysis is crucial because it models the belt as a series of connected springs and masses.
So it simulates the stretchiness in the wave.
Exactly. It lets engineers predict those peak tensions during stops and starts. It can simulate if the belt might lift off the idlers on curves or sag too much. It even helps analyze the risk of the material itself slipping on the belt during acceleration or braking.
And the results of that analysis directly feed back into the design.
Directly. It informs how steep the VFD's acceleration and deceleration ramps should be. It dictates the precise profile for the soft braking system, maybe multiple stages of braking torque. It's all about designing for how the system actually behaves dynamically, not just how it sits still. It's fundamental risk mitigation.
That's fascinating. And they even model the material being carried.
Yeah, often using a technique called the discrete element method, or DEM. This simulates the behavior of thousands of individual lumps of ore or particles.
Why go to that level of detail?
Mainly to optimize the design of transfer chutes, where material moves from one belt to another or from a feeder onto the belt. DEM helps design the chute geometry for a smooth, centered flow of material. This minimizes wear and tear on the belt, reduces material degradation, prevents spillage. It's about optimizing the interface between the material and the machine.
Okay, so this tech isn't just theory. It's out there working at huge scales. Can you give us some real-world examples? Where is this happening?
Oh, yeah. The absolute gold standard, the one everyone points to for megawatt scale regeneration, is the Los Pelambres copper mine in Chile.
Los Calambres. Okay, what's the setup there?
It's actually 3 downhill conveyors linked together. They stretch a total of 12.7 kilometers, that's almost 8 miles, and they drop a staggering 1.3 kilometers vertically, over 4,000 feet.
Wow. And the power generation from that drop.
When it's fully loaded and running, that system can generate up to 25 megawatts of electricity.
25 megawatts from a conveyor belt.
From gravity, essentially. That's enough power for tens of thousands of homes. It supplies a really significant chunk of the entire mine's electricity needs.
That's incredible. What kind of specs does it have?
It moves 12,000 tons of ore per hour, uses 11 huge 2,500 kilowatt motors. The belt itself is that super high-tension ST7800 steel cord belt we mentioned, running at 7.5 meters per second. And the control system is state-of-the-art. Closed-loop tonnage control, variable speed, sophisticated load sharing between the motors, and multiple layers of braking, 5 mechanical systems plus 3 levels of motor control braking. It's a beast.
25 megawatts. Mind-blowing. But what about smaller operations? Is this tech only for the giants like Los Pelambres?
Not at all. It scales down quite effectively. Take a lignite mine in Poland, for example. They put in a 565-meter conveyor, much shorter, with about a 70-meter vertical drop.
And that still generates useful power.
Absolutely. It generates about 790 kilowatts on average. That works out to around 1.6 gigawatt hours of green electricity per year.
Okay, significant. But what about the economics for a smaller one like that?
That's the compelling part. The projected payback period for that project was just 3 to 4 years.
3 to 4 years. How?
Primarily because the cost of grid electricity in that region was quite high. So every kilowatt hour generated by the conveyor directly displaced expensive purchase power. It shows that even smaller downhill runs can be really attractive financially, especially if local energy costs are high.
So it's not just for brand new mines either. Can you upgrade older systems?
Definitely. There's a great case study from an alumina plant. They had an old conveyor system from the 1980s. Its emergency braking was pretty crude, uncontrolled, frankly dangerous.
How did they do?
They did a major overhaul. Replaced the old synchronous motors with modern VFD-grade induction motors, put in a new regenerative AFE drive panel, and, crucially, installed a new PLC-controlled soft braking disc brake system.
And the result of that modernization?
Night and day difference. They got full programmable control over stopping. It drastically cut the dynamic forces on the belt during stops. Get this, the big counterweight used for belt tension. It used to violently jump 8 or 10 meters during an emergency stop.
Whoa.
After the upgrade, it lifted less than 2 meters, nice and gently. It completely eliminated uncontrolled run-out situations, made the whole thing much safer, much more reliable. A perfect example of modernizing existing infrastructure effectively.
That's a huge improvement in safety and control.
Yeah.
Okay, let's maybe try a hypothetical to really nail the energy numbers. Say you have a medium-sized 300-kilowatt downhill conveyor.
Yeah.
How much energy are we really talking about saving or generating?
Okay, let's run some rough numbers. A conventional system for that duty, maybe one with dynamic braking but not regenerative, might still consume energy overall, say around 142,800 kilowatt hours per month, just managing the braking and friction.
Okay.
Now, you replace that with a regenerative AFE system. Let's assume it operates at 90% capacity. It wouldn't consume power. It would actually produce a net output of maybe 188 kilowatts.
Producing 188 kilowatters.
Over a month, that's about 89,500 kilowatt hours generated and sent back to the grid. So you go from consuming over 140,000 kilowatters to generating almost 90,000 kilowatters.
That's a massive swing.
It is. It's not just about using less energy. It's about becoming a net energy producer. Compared to even a non-regenerative but electrically braked system, that's an overall energy saving in the ballpark of 37%. Significant.
Which brings us right to the bottom line, doesn't it? The economics, the financial side. This tech clearly needs a bigger upfront investment, right? Higher capital cost.
It typically does, yes. The capex for a regenerative conveyor is generally higher than for a conventional one. You've got the more sophisticated AFE drives, the advanced controls, potentially higher spec motors and brakes.
Can you give us a rough idea?
It varies hugely, of course, but for maybe a high 1,000-foot underground system, you might be looking at somewhere between, say, $275,000 and $400,000 fully installed. Key costs are the structure, the high-tension belting, and the drive package motors, the regenerative VFDs, which can be 50-60K for a couple of 300 HP units, plus the control panel.
Okay, so a bigger investment up front. But the operational costs, the OPEX, That must be where the story changes, especially compared to something like haul trucks.
That's exactly where the long-term value really kicks in. Let's do a quick comparison. Say a 40-ton haul truck versus a similar capacity 42-inch regenerative conveyor.
Right.
Truck CapEx might be $300,000, depreciated over maybe 7 years. Conveyor CapEx might be $250,000, but depreciated over 20 years or more, operationally. The truck burns maybe $56 an hour in fuel and maintenance, needs a driver every shift, high maintenance on engines, transmissions, tires, plus emissions, maybe 54 pounds of particulate matter per year. Your cost per ton moved could be $0 or 43 cents to 57 cents.
And the conveyor.
The regenerative conveyor. Its main operational cost is electricity, which it might actually be generating. Let's say it consumes power at 0.08 cents per kilowatt-hours when needed, but generates when possible. Needs minimal supervision. Maintenance is lower idlers, pulleys, the belt itself. Emissions, way lower, maybe 3 pounds of particulates per year. And the cost per ton, down around $0.0306.
3 to 6 cents per ton versus almost 50 cents.
The difference in operational cost is just enormous. And that difference adds up dramatically over the 20-plus year life of the conveyor system.
So the really big financial lever here is displacing purchased energy, or maybe even generating revenue.
Absolutely. For a mine connected to the grid, it's straightforward savings on their electricity bill. But think about remote mines, off-grid operations running on diesel generators.
Where power is super expensive.
Exactly. Diesel power can cost anywhere from $0.1050 to over $1 per kilowatt hour in really remote places. So every single kilowatt hour generated by that downhill conveyor directly displaces incredibly expensive diesel fuel. That slashes operating costs and makes the payback incredibly fast.
Right. You mentioned those fast payback periods, like that Polish mine.
Yeah, payback can definitely be as short as 3-4 years in good conditions, often under 5. More detailed analyses using things like life cycle cost, LCC, and net present value, NPV, consistently show strong long-term financial viability.
And that hypothetical 300 kilowatt conveyor, what did the payback look like there?
Remember those numbers. Investment around $200,000. If it displaced diesel power costing, say, 0.30 cents per kilowatt-hour, the annual energy savings were over $322,000. That gives you a simple payback period of just 0.62 years.
Less than 8 months.
Yeah. When you're displacing expensive fuel, the economics can be incredibly compelling. That kind of return gets attention.
For sure. And beyond the direct dollars and cents, this also plays into the bigger picture, things like ESG targets, environmental, social governance.
Big time. Replacing diesel haul trucks, that's a massive reduction in direct carbon emissions. Less dust, less noise pollution too. Generating clean energy on-site boosts a company's sustainability credentials.
Which can help with their reputation, maybe even financing.
Definitely. It improves their social license to operate in the local community. And yes, it can potentially open doors to green financing initiatives or ESG-focused investors. These systems are part of a growing trend, a key technology in the expanding global conveyor market.
So, it really seems like an integrated win, economic, environmental, operational.
Yeah.
But okay, with all this advanced technology, it can't all be smooth sailing. There must be challenges, hurdles to overcome when putting these systems in.
Oh, absolutely. There are definitely significant challenges. Perhaps the biggest one is a mindset shift. You have to realize you're not just installing a conveyor, you're installing a power plant.
A power plant.
A variable power plant, specifically. Because its electrical output goes up and down directly with the amount of material on the belt, it must be treated as a power grid engineering project. It has the potential to impact, even destabilize, the mine's electrical grid, especially if that grid is small, isolated, or maybe a bit weak.
Okay, so grid integration is a major hurdle. You mentioned power quality before harmonics specifically. Can you remind us what those are and how they're managed?
Right, harmonics. They're basically distortions on the smooth AC electrical waveform caused by the rapid switching of the power electronics inside the VFD. Too many harmonics can cause issues like motors and transformers overheating, interference with communication or control systems, just general inefficiency.
And the fix?
As we discussed, the best fix is using active front-end, AFE, drives from the start. They are inherently low harmonic, typically under 5% THD, which usually meets even strict grid codes. If you don't use AFEs, you might need to add external harmonic filters, either passive ones like reactors and capacitors, or more complex active filters. But AFEs are generally the preferred solution now.
Makes sense. What about the other stability issue? The fact that the power generation level itself fluctuates with the load?
Yeah, that's a big operational challenge. If the material feed stops suddenly, your generation instantly drops to zero. There's a big surge of material, you get a surge of power generation.
Hmm.
In a small or isolated grid, these swings can cause voltage and frequency to bounce around unacceptably.
So how do you smooth that out?
The most effective solution, increasingly, is to pair the regenerative conveyor with a battery energy storage system, a BES.
A big battery.
Essentially, yes. The battery acts like a buffer. It can absorb excess power during surges and discharge power during dips, smoothing out the net power flow to the grid. Other strategies help too, like really good closed-loop tonnage control on the feeders to keep the material flow onto the belt as steady as possible. And for remote mines, integrating the conveyor into a larger hybrid power system, maybe with solar, wind, and some backup diesel, creates a much more resilient overall energy setup.
Okay, batteries and smart controls. What about just keeping these complex systems running reliably long-term? Maintenance.
That's definitely a consideration. These are sophisticated systems. They need technicians with the right skills, but the mitigation strategies are pretty well established.
Like the condition monitoring you mentioned.
Exactly. Leveraging all those sensors for predictive maintenance is huge. Using data analytics to spot developing problems and schedule maintenance proactively before something actually breaks, that maximizes uptime. Also, standardizing components using the same type of motors, drives, brakes across multiple conveyors, if possible, simplifies spare parts inventory and training.
And training itself must be key.
Absolutely essential. Investing in proper training for the mine's electrical and mechanical maintenance crews is critical for the long-term health and performance of these systems. They need to understand how these components work and how to troubleshoot them effectively.
This has been a fascinating deep dive. We've gone from seeing downhill transport as just a cost to understanding how it could be, well, a power plant and a source of profit. Just to quickly recap the big takeaways, these regenerative systems turn material movement into energy generation. They offer really significant economic wins, especially for remote mines burning diesel. Plus, they're safer and much better for the environment.
That sums it up well. And based on the sources we looked at, there are some really crucial pieces of advice for any operation considering this. First, always do a thorough, holistic feasibility study. Look at the terrain, the material, the power situation, the economics, everything. Second, for any long or high-tension conveyor, dynamic analysis isn't optional. It's essential risk management.
Right. Got to understand those shock waves.
Exactly. Third, specify AFE-based drives as your default. The benefits for efficiency and power quality are just too significant. Fourth, demand fail-safe mechanical braking, but make sure it includes PLC-controlled soft braking for smooth, safe stops. Fifth, do a grid impact study early on. Treat the conveyor like adding a new power source, and seriously assess if you'll need a battery system, a BES.
And finally,
Build a solid, maybe even conservative, financial case. Be sure to properly value the cost of displaced energy, especially if it's diesel. And don't forget to highlight all the positive ESG, environmental, social, governance benefits. They matter more and more.
it really is a transformative technology, changing a fundamental part of mining.
And potentially other industries, too, where gravity plays a role.
It really makes you think, doesn't it?
It is.
If we can take this simple, unavoidable act, moving stuff downhill,
Yep.
and turn it into a power source, what other things that we currently see as just costs or liabilities in complex industrial processes are just waiting for some innovative engineering, maybe a fresh perspective, to be turned into surprising assets?
That's a great question to ponder.
Something for you to think about until our next deep dive.